Thank you very much, Christian, for this very kind and nice introduction. Good afternoon, everyone. I would have loved to be with you, but it was not possible for me to constraint on my side. I hope I can do it next time. So thank you for giving me this opportunity to present this work on learning risk metrics using neural networks. So this is something mixing statistical learning plus risk management, and we have a test on real data coming from cryptosphere. Okay, so it was done with my colleague Michael Alouche from Kaiko. So the Kaiko is a data provider, big data provider for crypto data, and Stéphane Girard is a research director at INRIA at Grenoble. And this is in the work done in the framework of stress tested. This is a big initiative we've funded by BNP Paribas. It started 6 years ago. It will run till 2028. And so this is very fruitful collaboration. So if among the students here, some of you are interested in a postdoc or PhD grant, okay, we can offer this thing. So I like now to dive into the talk. So let's say yes. So the risk management context is quite clear. You see that after the financial crisis in the 80s, regulator banks have promoted some way to better monitor the risk, to share a best practice in risk management. And so they promoted the value at risk, which is essentially quantile on the loss of the portfolio. Okay, so this is a loss of a given horizon, and the loss will occur with a given level of confidence. Okay, but major criticism on this value at risk come from the fact that it does not incentivize the diversification of risk. Typically, it doesn't fulfill the sub-additivity property, so making these risk metrics a non-current measure. And so also quite obviously, since this is a quantile of a loss, of course, we don't care about the possible loss beyond the quantile. And so, okay, so there's a chance to lose something, but in fact, the magnitude of the loss is not quantified. So years after years, regulators have and academic people investigate alternative or improvement of around this notion, and they come up with the solution of conditional value at risk. That is something averaging the loss conditionally to excess to be larger than a given threshold. Okay, and this conditional value at risk became the expected shortfall. And now this is a standard in the regulation. Many banks have to compute it, and regulators monitor this expected shortfall. So we need measures of this type. So now on the mathematical side, quite easy definition. So the var is a quantile. So this will be a quantile of a loss. So here the loss will be defined as a positive quantity. So you see that here the alpha of interest will be small. So alpha will be close to 0, so that we will look at the quantile, the right quantile, I would say, the quantile on the right part of the distribution. Okay, so it means the loss are, we change the sign and this becomes positive. The expected shortfall is the average of the quantile between 0 and alpha. And since we assume that the CDF is continuous, then this is the same as computing the conditional explanation of x given by x is greater than the value at risk. Okay, so this is everything is definition could be different, but at the end, quantities are the same under the condition that everything is continuous. That is, the CDF is continuous. And here we are we are extending a bit this notion by considering conditional tail moments. That is not only the first moment, but in fact any moment of order p. Okay, and so the context is to try to have a statistical learning procedure just to learn what is this CTM, the conditional tail moment of order p, CTMP, at order alpha n or at level of confidence alpha n, but in a specific setting where n alpha n goes to 0. So this is in a case where we are out of sample. Typically, we're going to learn these risk metrics given a sample. So let's say you have n data points. If you just order the data points, if you compute the order statistics, then of course, in sample, we're using in sample estimation, what you can estimate at in the best case correspond to the quantile of order 1 over alpha n equal 1 over n, meaning that you are in a situation n alpha n equal 1. So the maximal value you have in the data is correspond to n alpha n equal 1. So here we want to go beyond this maximal value, and so it means that we are looking for estimation of risk in a situation we are really considering the tails far away from zero in a way, or far away from the bulk of the distribution, really in the extreme right of the tail. Okay, so on the background result, we have been working on these kind of issues recently, where for the VAR, we have seen, and this will be an ingredient coming into the picture, that for the VAR, if we want to parameterize in a proper way the VAR using neural network, in fact, the good way to proceed is not to using ReLU activation function, but in fact, a ELU activate function. Okay, so the ELU, this is positive, this is straight line on the positive part, okay, and on the negative axis, this is an exponential. Okay, so this is a kind of modification of the ReLU function. But in fact, the ELU activation function gives a natural representation of extreme quantile with a very low bias. So it is one of the major achievements of this work. And so, of course, we will incorporate this ingredient in our analysis. Still on the background result, if you are interested to compute in computing the expected shortfall, either you use a parametric approach or a non-parametric approach. So parametric approach, that is, you believe that your data come from a parametric distribution with a few parameters. So it can be there are some works related to elliptical distribution, to five-side distribution. There's a list of distribution for which you can compute explicitly the expected shortfall, doing just explicit closed form integration. Okay, this is here, so you can deal with Pareto, student, Fréchet, inverse gamma, Burr, general Pareto distribution, Fishner-Sendeker. So this is the list of distribution for which you have an explicit expression for the expected shortfall. Okay, but of course, you never know if your distribution fits one of these assumption. Okay, so sometimes people prefer to use non-parametric estimators. So this is the topic of these slides. So typically, what you may try to do is to replace the TMP. So that is the conditional pif moment beyond the VAR by this average over the order statistics. So you're going to rank your data, take the largest one. So here it will be the n alpha largest one. The rank n alpha correspond to the empirical quantile at level 1 minus alpha. So you just average your data over the largest values, and then this is the natural empirical counterpart of your theoretical conditional tail moment of order p. There's some modification of this because this is the conditional version, so you can use kernel estimation. There are various tricks. There's also some asymptotic properties for analyzing this estimator. But in our situation, that is, we are considering extreme risk. So that is the alpha we are considering, or the number of data we are considering, is such that the maximal value on the data set is below the quantile of interest. So of course, in that case, you have no data. If you consider such alpha, you have no data arising in this sum. So of course, you can implement this empirical estimator. Okay. So this corresponds to situation typically to either alpha is very, very small, Okay, so you look to extreme right tail, or the number of data you have is quite small. Okay, so maybe just 100 or 200. And you will see example at the end of the presentation where I will give you example where the n is smaller than 100. So you are in a situation in that case where you have to compute value at risk or expected shortfall at the level 1% or 99%, okay, but with less than 100 data. Okay, so you have to do something. So really, the context of our work corresponds to an extrapolation in detail. So we are not in a situation of just estimation, interpolation, in sample estimation, but we are really in a situation of extrapolation beyond the maximal value of what we have observed in a context of evitel. So what we try to do is try to make the connection between this out of sample extrapolation, out of sample because we try to compute something which is far away from what we have observed using in sample observation. Okay, I think this is the key words in the presentation. And to achieve this this trick, I would say, we will take advantage of extreme value theory just to make the bridge between what appears in the extreme, in the not too extreme, and in the really extreme points. Okay, just a few illustrations about why we have really heavy tails in the data. So here this is an illustration coming from crypto market. So since Kaiko is a major data provider in crypto market, this data come from Kaiko. Here this is data on centralized exchange, but they also provide data on decentralized exchange. So there are many crypto assets. I'm not going to dive into this, but here we are considering a list of 67 pairs here over 4 different days, corresponding to calm, stress, and calm period. Okay, blue and orange stress, and calm green and red calm period. Okay. So you see when we are in a calm in a stress period, the number of trades per minute is rather higher than when this is a calm period, of course. And also the analyzed volatility is higher in a stress period than in a calm period, obviously. Okay. So in total, you see the number of use cases we have, 4 times 67, and the number of data points we have is about 80 millions. So what is important in what I'm showing is that the computation of the tail index parameter. So the tail index parameter, we're going to explain it a bit later, but this is a measure of how heavy is the tail. So typically, if the tail index parameters gamma, this is usually denoted by gamma, is close to 0, then we have very light tail. Okay, so you have any moments of any order, and if gamma is strictly positive, then essentially you have a finite moment up to order 1 over gamma. So gamma equal 1 correspond to so typically gamma equal 1 correspond to data having a finite expectation. Gamma equal 0.5 corresponding to data having a finite variance, and so on and so on. So here, this corresponds to the box plot of different tail index. So different days, the stress period here, the calm period here, and this is a box plot because so we have many points because we have many crypto assets. Remember that we're considering 67 pairs here. So here is the distribution of tail index over 67 pairs, and you see that in any case, indeed, whatever the pair, we have a gamma which is around 0.5. So the variance is more or less finite, but we can't expect much more from a finite moment, in fact. So really, in financial data, we have to live with heavy tail distribution, and so we have to account for this heavy tail in computing risk metrics and so on. So now I'm going to dive into the methodology. And I'm first going to give you a quick overview of the statistical learning approach with a few results of coming from extra value theory, just to help you to better understand what we are doing. And then I will give a few theoretical results in that direction. And then I will go to the numerical result. So we are working in the Evitel distribution. So we are in the domain of attraction of Fréchet. This is usual to consider the quantile in normalized way. So that is, we consider the quantile of y minus alpha, but alpha will be reparametrized by 1 over t, and t will be large, so that 1 over t will be small. Okay. So this u function corresponds to the tail quantile function. And so when we are in a Fréchet domain, it corresponds to say that this quantile behaves like a power function, so 2 to the gamma, t to the gamma, and gamma is the tail index. Okay, I've mentioned before on the previous slides. So the quantile is like t to the power gamma times a slowing varying function. Okay, this is the definition. This, if you can't remember. Okay, and so once you plug this parameterization into the definition of the CTM here. So this is CTMP. There's a typo here. That is the average of the p power of the quantile. With basic manipulation, what you get is simply that the log of the CTMP of order p at level 1 minus alpha will be given by the p times the log of the quantile at level 1 minus alpha plus an extra function, which is psi p defined here. So this is just basic manipulation here. There's nothing complicated here. So what you see that what we need to learn from a statistical point of view is both computing the quantile here, learn the quantile from the data, and we are still in a situation where we are out of sample. So in fact, for the alpha we are interested, there's no data at that sample here, and also we have to learn this function. So we have to learn two quantities. So to understand what is the strategy of predicting what is the CTM at level P, in fact, we are going to consider two confidence level, alpha and delta. Alpha for the outsample level we are targeting, and delta n, the in-sample one, on which we're going to compute quantities. So we're going to write the difference between the two like this. Okay. Here I'm going to replace the value of Q by using this representation with L. Okay, so the tail quantile function is given by t to the gamma L of t. So I'm going to replace this, and so that's why I have this expression here. The difference of two CTMP. There's still a typo here. This is something linear in the log spacing, log delta n divided by alpha n. Okay. Plus p times a function of the log spacing and the log 1 over delta n. And this function, this is simply given by this formula here. This comes just for the basic manipulation here, plus the psi p function here. So just a quick look to this. So what we need here is that the alpha n is between 0 and 1, of course. The delta n will be between 0 and 1. No, so yes. And this term will be positive because delta n is greater than alpha n, and delta n is smaller than 1. So both quantities are positive here. So we need to learn, in a way, this linear part, this unknown part, which is a complex function related to the slowing varying function, and the psi p function here coming from that definition. So how do we perform how does it work from the statistical learning point of view? So what we need to learn, in fact, maybe I'm going to be back to this slide. In fact, what we're going to do is to provide an estimation of this quantity, the CTM at level 1 minus alpha n. We're going to compute an in-sample estimation of this conditional tail moment of order p. for in-sample estimation, we can do it because this is typically in-sample. So we can just average the largest order statistics. So we have an estimate for this. And we have also to compute this quantity, which we don't know. Okay. So what I'm going to show now is how we compute all these function, these unknown function here. So this unknown function, typically this is that difference. We don't denote it SIK. Okay. This is a function GP function, just to make it simple, at level 1 over I over n and k over n. So here, look, this is the log spacing in a way, the log CTM, but computed at in-sample points. So here, I and k are just something larger than an integer greater than 1. So here, this corresponds to the definition of this for in-sample quantities. Of course, we have an access to this quantity using the data. So they have an empirical version of this. So this is just the average of the peak moment for the largest values, for the ith largest value or del k largest values here. And for the neural network approximation, we will try to find the best function GP, mimicking, reproducing this estimation here. Okay, and the input of the neural network will be this quantity I over n, k over n, which are numbers between 0 and 1. Okay, and so once we have learned in a way to how to which function approximate in the best way this quantity, then we have a final estimation on our conditional tail moment of order p. It will be simply the estimation of this in-sample CTM, this is that one here, multiplied by the exponential of this function here. And then we're going to replace the in-sample level rank here by the out-sample we want, and we're going to keep the in-sample we need. Okay, so this is the global strategy. I think everything is said here. So what can we bring from the mathematical point of view now is we can try to think about, is it possible to well approximate this function phi here, this function psi p using neural network? This part is quite easy. This is just a linear function. Well, this is just a linear part with a feature log of k over I. So this is quite easy. The feature is known. We just don't know the coefficient here, but this is something we can learn on the in the learning procedure. So the question I want to address now is it possible to well approximate the phi and the psi p here under some assumption? Okay, for the first function phi, how to approximate the phi using a neural network. For this, we need assumption on the distribution of the points. So what we are going to assume is a standard assumption that not only we are in a Fréchet domain with a tail index parameter given by gamma, so there's a gamma so that we are in the Fréchet domain with that tail index, but also we have a second order condition, we have a third order condition, we have a fourth order condition. Okay, so we have a Jeff order condition, and this Jeff order condition describes the way the slowing value function will converge to zero or to constant, and how its derivative will converge to zero. So in fact, there's nothing new here. This is a standard assumption in the literature of extreme value theory. They say that essentially the Jeff order condition says that we can decompose the log of this of the ratio of this slowing value function as a sum of product of a function of t and a function of z here, and the z is a power law described by some coefficient, by some exponent, which we call the Jeff order parameter. So the Jeff order parameter systematically they must be negative. It is a consequence of the structure behind the slowly varying function here. So the rho j here must be negative. There are many orders, okay, and so the structure is of this type here. And so the result we have is that the function of interest phi can be very well approximated using this setting by a neural network using not a ReLU activation function, but ELU activation function. This is something quite important in the analysis. So under the assumption, if you specify a bit what is the AJ, which is also a standard hypothesis, okay, then what you can do is really write phi as a summation of our different weights of a difference of activation function, the ELU activation function of the entries x1, x2 here, plus something which is small here. And the small term here can be described very well in terms of the G order condition here. So the first result is that this complicated function can be naturally represented as a neural network with ELU activation function. The second function we are interested in, remember, I come back here. This is that function here. Okay, what can you say about this function here? In fact, this function, if we still in the context of second order condition or similar version of this, okay, I would say, we can have some result on this. So typically, this function is smooth in the sense that there is a C1. So in fact, if you usually we assume that the L is a C1, is a slowly varying function of class C1, okay? Then there's no problem to differentiate this psi p respect U because everything is made so that you have the derivative of this will be well controlled, well integrable, okay? So no problem of differentiability away from zero here, all right? And additionally, we can extend this function, which is well defined on 0, 1, 0 excluded, to a continuous version on 0, 1 with 0 included, because we can compute the limit when at 0 this function here, which is not systematically the case, because you see that there's a 1 over u here. So when you should send u to infinity, u to zeros, you may be in trouble here. So this is one result here. In fact, this result in the context of Fréchet domain of attraction is quite standard because it allows you to retrieve well-known approximation, causing to say that in fact the conditional tail moment of order p can be approximated by the quantile at order p times a correction term, which is just 1 divided by 1 minus p gamma. Okay, so there's a correspondence between the expected shortfall and the quantile, or the conditional tail moment and the quantile. So here, the function psi p is continuous, but in fact, we can do a bit more by showing, in fact, this is also order continuous function with order regularity, which depends on the second order parameter, in fact, the absolute value of ρ2. Remember that ρ2 is negative systematically. So in fact, we have to always to consider the absolute value of ρ2. Okay, so psi t is order continuous. This is a function defined on 0, 1. Okay, so now this is quite easy. You want to you wonder if you can approximate this order continuous function by a neural network. Of course, you can by just considering a piecewise linear approximation of this function, and consider a piecewise linear approximation of function is just taking a ReLU neural network approximation of the function, okay, with appropriate number of neurons. So of course, we can do this. So at the end, the global result is the following. the global result is the following. So now if we not only consider the second order approximation, but we can go up to the Jth order condition. So we improve a bit the result I've shown, okay? We consider a P which is so that the CTMP is well defined. So we can take a P too large according to the gamma here. Then we can find a neural network approximation made of partly ReLU neural network, partly made of ILU neural network with some prescribed number of neurons. Here K1 and K2. Okay, so K2 is related to the assumption, the number of for my Jth order condition here. So there's a neural network based on ILU and ReLU, so that the approximation of the CTMP in log scale by this neural network is well controlled in that sense. So there's a decay as 1 over K1 to some power. So the larger the number of neurons you consider for the ReLU approximation, the better the approximation you get. And here, it is something related to the ILU approximation. So if you have higher order condition, higher order condition for my distribution, then you see that the rho J here, the rho bar J here will be very high here, and so it will be very accurate. Here we will have something very small. So this is the global approximation we can get from this. And so in a way, it is a guarantee that using this kind of parameterization, you are able to compute the unknown quantities with a given accuracy. So you can control the error tolerance in a way using this kind of parameterization. And so once you have this, of course, the final estimator will be, as mentioned before, the in-sample conditional tail moment. So you just average the kth largest value of your data set with a power P here, and you take the exponential of the learn function I've mentioned before. Okay, and this learn function is simply that one here. So we have learned that one, we have learned that one, and also we have learned just the basic feature here. And so everything is done. Well, I don't know how much time I have, so I think I started 35 minutes ago. So I think I can give you, I have time for, I'm going to take 5 minutes just to give you a quick overview of the kind of math we can put in the analysis, and then I will go to the numerical experiment. So one of the proof, I'm not just to illustrate how we use the assumption to get the result. So typically here, I'm just focusing on the proof where we want to analyze the regularity of psi p. So psi p is the ugly function here, where L is the C1 function, which is slowly varying. So remember, we had two results, two claims. It was the psi p was can be considered as a continuous function on 0, 1 on the closed interval, okay? And additionally, the psi p is the older continuous function with some parameter here, which is related to the second order parameter. Okay, so the fact that we can differentiate WP, I've mentioned this before. This is actually a differentiation under the integral. There's nothing special here because we are away from 0, so everything is fine. Okay, now we want to take the limit and to show that we can extend this to a continuous function when u goes to 0. So in fact, L is a slowing varying function. So when you take the limit here, you know that systematically here the ratio will converge to 1. In fact, you don't know what is the limit of L, but anyway, the ratio will converge to 1 because you have this assumption of slowing varying function. Okay, so inside the integral, this is converging to 1. Okay, so it remains just to show that what is inside the integral is well bounded by an integrable function, so that you can take the limit using a dominated convergence theorem. In fact, in the setting we are considering, since the L is slowly varying, you can use Putter bounds. So Putter bounds correspond to universal bounds on slowly varying functions. So a slowing varying function of order 0 typically is squeezed between two polynomial functions, one with positive exponent, one with a negative exponent, and the exponent can be chosen as close to 0 as you want. Okay. So using Putter bounds on these, then you can provide an upper bound on everything and then pass the limit inside the integral. So the continuity is clear. Now we like to move to the Hölder continuity. So what we know under the second order assumption is that the logarithmic derivative of L multiplied by a precise power relative to the second order condition. In fact, this is again a regularly varying function of index minus epsilon. So epsilon here is something small. This is just a parameter for the proof. We take any epsilon, any positive epsilon. So we know that under the assumption we have, the logarithmic derivative multiplied by this must be a regularly varying function with index negative. As such, the function is bounded, and so since the exponent is negative here, and so from this you can derive an upper bound on the logarithmic derivative. Once you have an upper bound on the logarithmic derivative, then you have a bound on the increment of the log of L by just by integrating this bound here, and you obtain this quantity here. Okay, so this is the first estimate here, where we use the theory of slowly varying function or regularly varying function. And now we can compute the increments of the psi p just to show the Hölder regularity. So this is the definition of the psi p. You just put outside the log this constant here because that does not depend on W here. So you have one term here and one term here. This term has been controlled here by this computation here. So you see that this term is already, we have already managed this term. We just have the increment of a function, of a power function here. Maybe the exponent is between 0 and 1 or larger than 1. But in any case, the increment of such function is bounded by this Hölder inequality, I would say, or Hölder regularity inequality. So this is okay for this term. And for this term, what we can do is using the similar bounds as before. So we have a control before on the increments of the log of L. So we have this thing. And when you translate this inequality in terms of bounds on the ratio of the LP, it gives this condition here. So you just take the exponential here, you get rid of the log, and at the end you obtain this thing. Okay, so you have a way to low upper bound and bound from below the ratio between the LP at different points here. So that when you want to compute the log of the difference of the log here, typically you can plug an estimation of the of that term here using the upper bound here. Okay, you obtain this term here. This term does not depend anymore on W, so you can put it outside the integral and the log. So it gives the log of the x of this, so it gives exactly this term, and it remains only that term divided by that term, so it gives a log of 1, so 0. And so this is it. And so you do the same with the lower bound, and at the end you obtain the Hölder inequality for the psi c function. And so of course you can repeat this kind of computation for getting higher and higher, more and more accurate term, I would say. Okay, and last thing, but I think I'm going to be fast on this, is that you know this basic result is that when you have a Hölder continuous function, if you want to approximate it by a neural network, you can use at the first order, you can use the piecewise linear approximation. Piecewise linear, this is just an approximation using a basis function, which is the add function. Okay, just 0. Okay, the add function, the triangular function. A triangular function is just a linear combination of three neural network based on one neuron, I would say, or three ReLU function. Okay, so at the end, of course, you can approximate any Hölder continuous function by linear combination of ReLU function and the number of linear combination depends on the accuracy you want. So you have this kind of relations. So I don't want to detail more of this. I think this is, you know this very well. So now I like to dive into the numerical result and to show how the estimator we provide behave on synthetic data and on a real data situation. So of course we want to compare our estimator based on neural network with different competitors from the literature. So we took the state of the art in terms of quantile estimation or expected shortfall. So the first thing we would like to compare with is the direct estimator. So that is, we take the in-sample estimation of the expected shortfall. So here we stick to the expected shortfall, so p equal 1. So we take the in-sample expected shortfall at the level k here. And then we apply a scaling factor just to go from the in-sample to the out-sample. So there's a ratio here because of the Evitel distribution. And the scaling exponent corresponds to the tail index. And we're going to estimate the tail index using the Hill estimator. So this is the basic solution, what we call direct estimator, like You can do a bit better by considering a modified Hill estimator, which has less bias than the Hill estimator. This improved Hill estimator corresponds to the corrected Hill estimator developed by Cairo, Gomez, and Pestana here. Asymptotically, it has the same variance, but the bias is smaller. So there's another estimator then. Alternatively, what you can do instead of estimating the in-sample expected shortfall, you can assume, use this property that for pressure domain, the expected shortfall can be connected to the quantile of your distribution. So this is exactly this. The in-sample expected shortfall can be related to the quantile multiplied by, adjusted by a factor related to the tail index parameter here. So in fact, we replace the in-sample expected shortfall by its approximation by a quantile modified by the tail index here. Okay. You can also do the same thing with a modified corrected Hill estimator. And alternatively, you can also use another estimation of the quantile, which is the corrected Wassmann estimator developed in Gomez and Pestana. Okay, so essentially we have this list of competitors. So on simulated data, what we have done, so we took data set of 500 points, okay? We have tested these on 7 Evitel distribution with different tail index gamma, with different second order parameter ρ2 here. Of course, in this Evitel distribution, it corresponds to the list of distribution of parametric distribution I've shown before. We know what is the exact value for the expected shortfall because we have a formula, so we can compute the error of the estimator compare it to the ground truth here. And to compute the error, we choose the median square error. So that is, we run several times the algorithm. So here we run 500 times the algorithm. For each one, we have an estimation. We compare with the ground truth. We compute a relative value, so we divide by the ground truth. Then we run it 500 times, and we take the median of this. Okay, and this is the result we have. Okay, so we compute for the extrapolation quantile. We consider the quantile at level 1/2n. Remember that the largest observed value is 1/n. So here we go further. So this is 1/2n or 1/10n. Okay. So typically the result we have is something like this, can be summarized in this kind of table. So you see that the different competitors, the method we have developed here, according to different gamma and ρ2 here. And you see, when there's no value here, it corresponds to the fact that the estimator are not able to provide an estimation which is accurate enough in the sense that the relative error is larger than 1. Okay, so in that case, you see that in some situation, none of the competitors are able to provide something which is realistic in a way. Okay, you see that here only the best when ρ2 correspond to -1. So when you increase the second order parameter, in fact, the corrected Wassmann estimator is the best. In fact, what is the idea? What is the behavior behind ρ2 equal -1? So you see that here, when ρ2, remember, this is something which is negative. So what happens when ρ2 is close to 0 compared to ρ2 very far from 0? In fact, we know in extreme value theory that when ρ2 is close to 0, the bias is huge. The bias in estimation of quantile of everything is huge, in fact. In fact, the worst situation from extreme value theory is to consider a second order parameter which is 0 or almost 0. This is the hardest situation in extreme value theory. So we see that in that case, the procedure we propose is quite efficient, in fact. And you see that other procedure can't provide something accurate. While when ρ2 is equal to -1, then the bias is significantly reduced. Okay, and then our complex procedure, I would say, can't beat the usual procedure, typically the corrected Weissman estimator. Okay, so that's right. But there's something interesting I will show you just after this. So this table is just an extract of more of a richer test or more of larger number of experiments. So typically here this is an experiment corresponding to different Bird, GPD, Fisher-Snedeker, etc. Correspond to different gamma and different rho. And you see systematically the same pattern. That is for when ρ2 is small, okay, typically none of the competitors can provide something accurate or something even realistic, and the procedure we propose is quite accurate, in fact. And when ρ2 is far away from 0 in a way, then the corrected Weissman estimator behaves quite well. So seemingly, it seems that our estimator is quite useful for this situation when a second order parameter is small. Now we can go further in the extrapolation. So this is at the level 1 minus 1 over 10n. Okay. So similar pattern, same thing for small second order parameter. The best is corrected Weissman, and our estimator is good, but not as good as the corrected Weissman estimator. There's something interesting to emphasize also. It is not only a question of accuracy. In fact, in all these estimators, there's a question of choosing the K. You remember that at some point we compute in-sample quantity. Okay, we compute typically the quantile, the in-sample quantile, or we compute the in-sample expected shortfall over the K largest values. So the choice of K in this method is really important, in fact. And so typically have a look to this the right panel of this figure. Here, this is the behavior of the relative median square error as a function of K. So here this corresponds to the competitors. Here correspond to our estimator. So you see the point. What I've shown before, in a way, is the best of this estimator when I've been able to choose K in a way. Okay. So usually the way we choose K is we plot the estimator, and when we see some kind of stability, so typically here this is quite stable here, and we say, okay, there's the kind of convergence, so let's pick a K around this value, and then this is our estimator. But you see the problem here is that when you change the K, the error can vary a lot for these competitors. So you are never sure about which K is the best. Whereas using the alternative approach I've been proposing in this talk, we see that the impact of the K is really minor. Okay. So in fact, I think this is a big advantage of the procedure we propose is the selection of the K is quite robust. You don't have to bother too much with which K do you have to choose. You see that here it could be a nightmare to choose the K. Here, this is, in any case, quite robust and quite stable. So I think this is a good feature of the method. And last to finish, just have a look to the clock. This is done now on real data. So here we have collected 7 years of data, 2016 to 2022, thanks to Calco data here. So here we take the log quantile plot. So just to, we have straight lines, so showing that in a way we are in a Evitel regime, so no point about this. Now I'd like to explain what is the procedure, just to show you what are the, of course we don't know what is the ground truth here. So we made a data-driven measurement of the error using a train and a test data set. So here we consider daily data over 1 year. So for every year, we're going to compute a risk matrix. Okay, so typically it means that we have about 360 data per year. Since we consider negative log returns, so it means that we have about 180 data per year. In here, the test, the trend data will be on 90% of these 180 data. So mostly the trend data is made of 162 data. So it means that the test is made on only 18 data. But these 18 data will correspond to the highest values in the data set. So what we're going to do? We're going to learn the exit shortfall at the level of the maximal observed data points. So the trend set as the maximum, and we like to compute the expected shortfall above this maximum. And to check if our extrapolation rule is accurate, we're going to use the 18 data points. We're going to average these 18 data points to benchmark the predictor we have using the 18 largest data points. And this is the way we're going to measure the error. And so the values is like this. So once again, there's a dependence between, according to the way you compute the in-sample, you compute the in-sample quantities. So you see there's an impact on the K. So still with the purple plot corresponding to our estimator, the estimation is quite stable. Okay, so there's no big deal about the choice of K. Take one and it will be good. Okay. Here correspond to the test estimation. So this is the average over the test value, and here correspond to the behavior of different competitors. So you see that according to the K, their behavior are really not stable at all. Okay, so it's really hard to select what is the K for which this is quite stable. So here you see that there's a kind of stability here. So you'd like to consider maybe something around this. But then you see that the predictor is quite far from the true value or the empirical value here. And so it was for the year 2022, and for the other years you see the other behavior. So we see that the purple estimator, our estimator, is quite close to the empirical one, while the other estimator are quite away from this. So I think it's a good numerical evidence that this neural network approximation behaves quite well. So to conclude, we have designed a neural network approximation to compute these extreme risk metrics, like shortfall or conditional time moment. We provide also some rate of convergence for the approximation. So we have a uniform convergence rate according to the number of neural networks, or according to the J-Further condition. Clearly, there's a very good performance of the new method compared to the competitors. But not only this, I think the main point also is that the way which we select the K is much more robust with this new approach than using the previous one. And we are currently working on the different extension of the method to have a conditional quantities or multivariate quantities. I'm going to stop here and thank you very much for your attention. I'm looking forward to your questions.
Thank you.